Hello everyone. In this paper, as the title suggests, anomaly detection techniques are used in the field of file type identification. Exclusively, our focus is on image type identification. The paper is presented in 5 different sections. First, we discuss file type identification and its application. In another section, anomaly detection is overviewed. Then the suggested framework for anomaly detection in image format classification is presented. Finally, an employment of the methodology is discussed. In the first section, we overview the concept of file type identification. We present a brief review of literature in image format identification. Then we mention how anomaly detection is missing from literature of file type identification, especially image file classification. File type identification is the first essential step in any application that we want to analyze or study the content of the files. Many methodologies have been used to identify a file format. The simplest method is extension-based method. In this method, we use the extension of the file to determine the type of the file. This method is easy and fast, but as it is clear, it is unreliable. An improved method is using signatures in the file. These signatures are not always accessible since many files do not have a signature, and in many applications we have a fragment. So this method is not very common. Content-based methods that use features that are extracted from binary content of fragments are popular methods in this field. As mentioned before, our focus is on image file format classification. Image format detection is a challenging but demanding task because there are numerous image formats and they are hard to distinguish from other multimedia files. In this slide and the next slide, we have summarized the literature review of image file identification. We don't mention the details of each research, but let's say that the techniques used for file type identification are evolving, and today researchers are using neural networks and deep learning for file classification. But image file format classification has not been the main focus of any work. And image formats were only a small portion of the data sets. There is an exception. My student thesis, Reyhan Fakuri, in 2019 used 10 image file formats. Unfortunately, the results were not very promising, but this is the only work done in this field. More importantly, no one has considered the possibility of having a file type other than the ones in the training phase. In other words, in so far applied methods, the main hypothesis is that all fragments under examination belong to one of the classes in the training phase. This assumption is invalid in most environments, and a fragment may not belong to one of the known labels. This indicates the importance of anomaly detection. With what has been said, So far, our contribution can be summarized in two main points. We have studied anomaly detection techniques in other fields of study and optimized them to classify image file formats. Second, we used a complete set of features resulting in a 577 lens feature set. In this section, we discuss the definition of anomaly. The challenge of anomaly detection is discussed in our context, and semi-supervised anomaly detection technique is introduced. Anomaly can be defined as patterns in data that do not conform to an expected behavior. Anomaly detection is the effort of finding these patterns or samples. In image format identification, any fragment that does not belong to an image file type is anomaly. Therefore, an anomalous fragment can belong to any other file formats. For example, it can be a fragment of an audio, a video, or text, or exe file, anything that comes into mind. It is impossible to entirely separate image files from other file types. We can't pull all image files under one uniform definition of the normal subspace. We have defined anomaly as any sample that does not belong to an image type class. This definition gives the anomaly class a large variety. In the picture, when we say labels, we mean labels in the training phase. As can be seen in this figure, anomaly detection methods can be put in three categories depending on the labels in the training set. For the nature of our work, we focus on semi-supervised anomaly detection. In semi-supervised anomaly detection, in the training phase, there are only labels for normal class, meaning the model is trained on normal samples, that is image file fragments in our case. Then in testing phase, normal and anomaly samples can be used to assess the trained model. In our application, the model is trained only on normal samples. In the test phase, some anomaly samples are used to evaluate the model. And also, it is obvious that some normal classes is used in the test phase. We have used autoencoder, a simple statistical method, and a distance-based metric for anomaly detection. We discuss them in more details in the next section. In this section, we introduce our suggested framework for anomaly detection in the field of file type identification. In this slide, we have shown our suggested framework for the training phase. An anomaly detector is added before the trained classifier. The training phase have two main steps. Training a model for anomaly detection using normal samples. This is a semi-supervised training. A scaling or feature selection step might be needed as well. Then we train a classifier with normal samples. Green boxes are the output of the training phase. In the training phase, we have anomaly detector, and we have some parameters for scaling and feature selection. The testing phase of the proposed method is shown in this picture. The input is a fragment. A fragment is first passed to the anomaly detector, and if it is determined as normal, it is passed to the image file classifier. Otherwise, the fragment is labeled as anomaly. To employ the framework, we applied three semi-supervised anomaly detection methods. First, we need to present the data sets. Our normal data set includes 10 different image types. Some of them were merged to form a more general class because the similarity between these classes. This results in 7 normal classes of around 2,500 image fragments. 80% of them are used in the training set. We have 25,000 image file fragments. 80% of them are used in the training set. Anomaly data set is composed of audio, video, and text. We have chosen these file fragments to be our anomalous data for the testing phase. Complete set of content-based features are extracted from the fragments, resulting in 577 lens feature set. As mentioned before, we have employed 3 semi-supervised methods. The first one is autoencoder. An autoencoder is trained on normal samples. In experiment, the test phase, it is expected that anomaly samples have large reconstruction errors. The setting we used is shown in autoencoder box. A simple statistical method is also used for anomaly detection. And object O is outlier if at least K attributes in this field, this is our features, of O have higher value than row standard deviations from the mean value. So in the training phase, the mean and standard deviation of each feature on the normal dataset is calculated, and for each feature, a lower and an upper limit is calculated. In experiments, if more than 58 features of fragment was outside these regions, the fragment is considered as anomaly. It should be noted that 58 is 10% of the length of the feature set. We have also used the distance-based method. We use commons for clustering with 10 clusters. In the training phase, the clusters are obtained from the mean and standard deviation of the distance of samples to the center of their corresponding cluster. A threshold is computed for each cluster. In experiment, first the cluster of the fragment is determined. Then, if the distance of this fragment to the center was more than the threshold, the sample is considered as anomaly. The table summarizes the applied methods. Here, the focus is on anomaly detection module, so we used a fixed and simple classifier. Random forest with 100 trees was used. Results are reported using 5-fold cross validation. The first row shows the case where no anomaly detection is used. The overall accuracy is 72%. In this case, anomaly classes are also labeled as one of the image file formats. Depending on the anomaly detection module, the accuracy significantly changes. There is a trade-off between true positive and true negative. This indicates the importance of choosing the right method for decision application. To report these results, we assume that there are equal samples from each class, but this assumption is not probably right for most environments. To show the importance of choosing the right method for the desired environment, we calculate weighted accuracy. In weighted accuracy, alpha defines the percent of anomaly in the environment. In other words, alpha determines the rate of the anomalous samples to normal samples. This figure shows the resulted accuracy by changing alpha from 0 to 1. We have plotted the three applied methods result as the plot suggests. Depending on the percent of anomaly, the accuracy of the method changes. This again shows how important the understanding of the environment can help the expert in choosing the best tool. This presentation can be concluded by mentioning 5 main points. First, semi-supervised outlier detection methods were utilized for applying in the field of file type identification. Then we presented a model for anomaly detection to use with the classifier. With a complete feature set and 10 image file formats, we applied 3 anomaly detection methods. The results show that the importance of choosing the right method for each application. Weighted accuracy was introduced to emphasize that the right choice depends on the environment, considering the trade-off between true positive and true negative, and the right tool for application. The expert with the understanding of the environment can be helped in choosing the best approach. Thank you for your attention. Good day.